Okay, sit down.
Can you see me? I'm
Yeah.
relaxing in the sun.
Okay, hello, Eric, hello, Ryan.
Yes.
Sit
Wow.
properly, please. Okay, so today we're going to talk about the how to search a value in a binary search tree. So do you still remember what's binary tree or binary search tree?
Yeah. Binary tree, yeah.
Binary tree, yeah. Binary
Two.
search tree.
Binary means two, right?
Yeah, to search tree. Remember the binary tree, right? The root some value, and you can have at most 2 kids, right? Each parent have at most 2 kids. This tree like upside down. This is the root. This is the leaf. Yeah, a leaf is leaf. Yeah, the leaf is a node without any children, right?
Yeah.
Yeah. How many roots can a tree have?
What?
Yeah, 1. That's the root.
Anyway.
And yeah, and then you can have many leaves. Yeah, this is like a tree. Yeah, right. Okay, so.
What are those two?
And this is a leaf. This is also a leaf. Leaf. This is just a normal node. It's not a leaf node. It's not a root. It's kind of a parent node of these 2, but it's a kid
That
to this
brown
root.
thing. That.
Yeah, remember this is their parent, but this is its kid, right? Yeah. So like Eric, Ryan, Daddy, yeah, Daddy and Grandma, okay? Something like grandparents, yeah? Daddy and Mommy, grandparents, yeah? You get it?
Mommy. But Mommy
Yeah.
has.
Okay, so look.
Take a deep breath.
So let's binary tree. And how about binary search tree? Do you still remember? The left nodes are always smaller than the parents. The right nodes are always bigger than the parents. Like, this is like 10, right?
10.
And this will be smaller, that will be 8, and this will be bigger, 9. And this will be 6, maybe this will be, maybe let's put it, no, this is 11, right? Bigger than that. And then this will be 9, something like that, okay? Right?
Yeah.
Smaller, always smaller.
But that one's supposed to be 7, right?
It doesn't matter as long as it's smaller. This is always smaller. The left nodes are always smaller than the parents. The right node is always bigger than the parents, right? But look, this is 9 is also smaller than 10, right? So what does it mean? It means that if we want to search 9, we compare the root. Is it smaller or bigger?
Smaller.
So which way does it go?
That way?
It's smaller. 9 is smaller than 10.
That way.
Yeah, so it should be smaller. It should be somewhere here, right?
Yeah.
Is 9 bigger than 8?
Yes.
So it's somewhere in the right hand tree, right? Because the right children is always bigger than the parents, right?
Yeah.
Okay? So this is the binary tree. So how we search it? We first of all define the class, remember? Class,
Yeah.
tree,
Yeah.
well, what's missing here?
Come.
Yeah. And then we can define a constructor, yeah? Remember constructor, initialization, and we can have this is the self, and then we have a value, right? And then we can have a left, and we can have a right. If we don't specify left and right, we can give it a default parameters, which is we can call it left, left. We can write left equals none. You know this none? None means nothing.
Yeah.
None. It means if you don't specify a value for left or right, it will be initialized to nothing. None. Okay. So then we can have this self dot value equals value. Self dot left equals left. Yeah. And what's am I writing here? Self dot what?
Right.
Right equals right, yeah? So
Yeah.
that means that the tree has three things. One, a node, yeah? A tree node has one value, yeah? It has a value. And it also have 2 things to point to its kids. It could be nothing. by default is nothing, right? Yeah, equals nothing, none.
Gone.
None. So it means that you can specify the left kit or right kit, right? Right? Yeah. Okay, so how can we search it? Define.
For when we write none, do we have to have a capital letter?
Yes, it's like true or false. True. For it's also these are called the special constants. Special constant. What do you call the nouns? Proper nouns, yeah?
Yeah.
Yeah, proper nouns.
Yeah.
Yeah, proper nouns start with the capital. Ryan, am I right? Ryan? Like Ryan and Eric are special proper nouns, yeah? Monday, Tuesday, Thursday, those are proper nouns start with T. Right? They are constants.
New York.
Yeah, New York. Okay, so
And 30.
search in the binary tree. Let's call it search, right? And we take a parameter root. This is the root of the tree, Eric. Root of the tree.
Yes.
And we want to search the value,
Yes.
right? Search the value.
We're searching for values.
Yeah. So how do we do this?
How do we do this?
Yeah. If the root is nothing, if it's you give me a none, right? Then if root is none, look, if the root is none, we return false, means we can't find it, right? Alright? Yeah?
Yeah.
Okay. Then if the value is smaller than root dot value, right? Dot value, remember the tree has the value, yeah? So what do we do now? If the root value is smaller than this tree, remember which is this is A, right?
The right one
10.
is bigger.
No, this is 10. We are looking for 9. The root is 10.
Then we go to the left.
Okay, so look, return. This is the magic. Return, search. We call the function root dot left, right? Root dot left. We are searching the left tree with the value, right? Else, what do we do?
Return search. Root dot right.
Not yet, because
No.
yeah, you're quite close. Remember, we haven't talked about when it's equal, right? Yeah.
Yeah.
So if value equal root of value, return what?
Value.
No, we already defined it. Return true or false. Return true or false.
True.
True. And now what should we return here? Return.
False.
No, yeah. We talking about
No,
left smaller.
bracket.
Yeah.
Root dot right. Value.
We're done. You see? So in this case, we always, when it's smaller, we search the left tree. When it's equal, we can move this.
That's
Yeah.
supposed to be right.
Oh, good job. Yeah. My mistake. Yeah. And then this can go here as well, right? It doesn't matter the sequence, right? If it's smaller, we search the left tree. If it's bigger, we search the right tree. Otherwise, it should be equal, right? Yeah. Then if it's equal, then we found it. Return true. If we find the root, remember, this is the leaf node, right? And it's still not equal to the value, then you will go to the leaf node dot left or right. Leaf node dot left, because leaf node does not have kids. So leaf node dot left or dot right will be none, right? Am I right?
Yeah.
Well, and then you call this function again, and root is none. What happened? Return false. Do you get it? And the value gets propagated, and then you will return false. This is recursive. Do you understand? Recursion, yeah? We talk about that on the lesson 1, recursion. Okay, so we can also do this using non-recursive method. This will be, will be something similar. Look, y, yeah, we're using the y root, yeah? This is the root, okay? This is the root. We are here, right? Y root is not long, right? It's not none. Y root is not long. Now we compare.
None.
If what? value, look, equals,
Um,
it doesn't matter, root of value, right? Then what we should do here? We found a value.
return.
Return what? 2, right?
Yeah.
We found a value. If value is smaller than root of value, what should we do now? If it's smaller, so what?
Return.
No, if it's smaller.
I go to the left.
Go to the left. Look, this is the magic. We can do this. Root equal root dot
Value.
left.
Left.
Yeah. And else, what should we do here? Root equals.
Root dot right. Well done.
Well done. And what should we do here? Return what?
Turn false.
Yeah, well done. Because after this, we still can't find the value. Then it must not be in the tree, right?
G looks like an E.
Yeah. Do you get it? It's easy, yeah? This is the way to search.
Wait.
Okay. So the complexity. Oh, what?
It's already been 11
Wait,
minutes.
Well done, L log n. Wow, how do you see log n? Yeah, because if they are every time I cut it in half, yeah.
Yeah.
Let's
It's
do.
already been 11 minutes and 37 seconds.
Let's what? Eric.
Yeah.
That's good. But okay, that's a special case. Look, listen. What's the special case? Look, this is good. I mean, log n. If there are 8 nodes, right? Or there are 1, 2, 3, 4, 5, 6, 7 nodes. Yeah? And on average, it needs the 3 times, right? 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Yeah? Do you get it? If there are 7 nodes, O log 7 is approximately 3. Yeah? Approximately 3. So it means it needs 3 times. Yeah? But how about if this is called a highly balanced binary tree? Means that, but what if a tree is balanced? You know the balance? Yeah, balance. Yeah. It means that at any level, the left, the minimum, and the right, the three levels, the difference is smaller than 1. That's called highly balanced. If this is not a balance, look, this is not a balanced tree. We don't have the left kid. We always had the right kid. Yeah? Do you get it? This is not this is not balanced at all. So this is still a tree. It just doesn't have a left kid. Yeah? So it's like a list. And if we want to find a value, in the worst case, we need to go through 7 times, yeah? And in that case, this will be O n. Am I right?
Yeah.
If the value is here, if we are 1, 2, 3, 4, 5, 6, you are finding the 7. And the computer needs to go through each list, the value, and it needs the 7 times, right? This is not balanced. But when we talk about the binary search tree, we have to talk about the balance. If it's balanced, if it's structured like this, then it's O log n. If it's not balanced, it's O n. Am I right?
Yeah.
Does it make sense?
Yeah.
Yeah, does it make sense? Okay, good. Rafi, good job today.
Oh yeah, babe. Oh yeah, babe. Oh yeah, babe.